where we're going to start today. And so, again, this is 1.2 of our notes packet, and we're going to talk about how to find out all of these different numbers from our periodic table or from an isotope symbol. So what is the most important number?
9.
No, Z.
Z.
That number up there.
It is the Z number right here, and that's the atomic number. This is going to be our number of protons.
Raiden, are you up?
What
Right?
happened?
I think your staple like caught on thing. I pushed it in all the way and it didn't go anymore. I think your staple cut. I'm so sorry.
Go away.
I'll punch your note packets for these class. That's crazy.
Do you want a sleeve?
No, I'm just gonna put it in Adobe.
It's okay.
It's already in Adobe for you.
Is it actually?
What?
Yeah, I've got PDF loaded into Canvas for you as
Oh,
of last
Do you
night.
want to swap packets?
So
Yeah.
you're welcome to do that. Just, I will always print off a hard copy. Okay.
I'm gonna do it.
So protons is going to be the Z number, and it is going to tell us the ID of our element. Okay, it's going to tell us what element we have. Along with that, we can get our electrons from that by taking the protons minus the charge, which I'll do. And that would be minus any negative charge or minus any positive charge. Okay. Our charge, we can figure out by looking at the protons minus the electrons. And that would help us with our charge. The charge could be given as well on any isotope. Again, here we're dealing with isotopes, not just our element symbols, okay? So we're looking at those specific isotopes that make up the element itself. What is an isotope?
It's like we got our element, and now it's like heavier, lighter.
Is every atom of carbon exactly the same?
No.
No, they have different masses. And typically we see carbon-12. That's going to be the vast majority of all of our carbon atoms that we see when we get a sample of carbon. That's why the average atomic weight is really close to 12, okay? But we also see atoms that are carbon-13 and carbon-14. And they're in a fixed ratio. Those mass specs that we looked at last night are going to, that's kind of how we figured out we had different isotopes of atoms. We started running things through mass specs and they ended up at different positions. It's all magnetic and you run it through a tube and
That's the fancy one.
positive ones
My
go
brain is
towards the
like-
top, negative, heavier ones go to the top. I'm sorry, other way. Heavier one goes to the bottom, lighter ones go to the top, and we can figure out what the percent abundance is from it. All right, so from this, we can get the element symbol. I'm just going to use X here to start with that because it could be any element. But again, we figure that out from the number of protons. We're always going to put the Z number on the isotope symbol down at the bottom. And we're going to put the charge up top. Our isotope name, we're always going to have our element in that isotope name. But then we need to talk about what mass of atom we have. And so that is where we're going to see what we call the A number. I always like to remember the placement of our A number and our Z number because it goes from A to Z on the isotope symbol. Okay. This A number does not show up on our periodic table because it's the periodic table of elements, not the periodic table of isotopes. So it's the full element. This A number is our mass number. And what two particles have the bulk of an atom's mass?
Neutrons and protons.
So we're going to have our protons plus our neutrons. And y'all, here I am with my color codes again. Red and blue make purple. I can't really do that with my electrons. Yeah, it's supposed to be purple. Let's see if I can get a better color of purple.
1 second, I gotta change that now. Sorry,
Nope, you're fine.
I'm like sitting over here thinking about it. It's okay, cause we're about to like get rid of this pack anyway.
What?
We're about to get like we're done with it in like 3 days, right?
Yeah, you're not getting rid of it though.
Yeah, keep
Yeah,
it.
but like we're not writing it anymore after like the next few nights.
But what if she wants to keep it?
I mean, yeah, but she's not gonna
I
keep it in
still
a
have all my
binder. She
chemistry
keep
notes.
it like digitally in like Adobe Scan.
I
Yeah.
could have done that.
Whatever makes your boat less dense. All right, so in order to figure out our
That's
neutrons,
a good one.
we're going to take the A number minus the Z number.
Cork boat. I'm not putting the line through my Z. That's weird. Unnatural.
I didn't on some of them, and I just did that last time. Thought I'd be fancy. So how do we find our average atomic weight?
We take percent of mass number, plus percent of mass number. We put it together, divide by the person. I don't know how
100.
to put it into words. I
Yep.
can show you, but
Nope, you're fine.
I thought it was
my
like
brain doesn't make sentences today, guys.
number
I'm
of
sorry.
protons times whatever they weigh plus number of neutrons plus whatever they weigh.
I mean, yeah.
So you're going to take your percent abundance, and you're going to times it
That's the term. That's the word. Yeah.
by the mass of the isotope. So I'm just going to put M there for mass of the isotope. And then you're going to continue on for however many isotopes you have. If you know your element, can you look up your average atomic weight?
Yes.
Yep. So if you know it, you can look at your periodic table as well. Like if you know what element it is. If it asks for you to calculate it, you better show some calculation work, okay? All right. Usually we would use that for an unknown, or to draw a mass spec, okay? So how do I know the number of energy levels in a neutral atom? Anybody remember?
It's a column.
Row.
What? Yeah.
It's one of those.
It's the
row.
horizontal.
It's the row.
It's not
It's the
a column.
horizontal row or the period on our periodic table.
Up, down, left, right.
The A star.
All right. And so notice here I'm saying for a neutral atom because if we lose electrons, we could go back some and go back to fewer energy levels. Okay. How did we figure out the number of valence electrons?
That's the column.
That is the group or the family, the column. So that's your family. And why do we call those columns families on the periodic table?
Similar.
The same
They
property.
react similarly because they have the same number of valence electrons. I should say they behave similarly in regards to chemical changes, not necessarily nuclear changes. Okay. Our elements. And then if we wanted to predict what the most abundant isotope is, what would we need to do?
Look at average atomic weight, right?
Spectrometry.
If you have mass spec, that would be great. Let's pretend we don't, though, at this point, and we just want to predict what the most abundant isotope would be.
Whatever is closest to.
Whatever the average atomic weight is closest to. So round it, okay? So this would be the element dash the rounded. Oh, wrong color. And I use AW for atomic weight, okay, just to abbreviate it a little bit. But it's your rounded atomic weight. Does that always give you the correct most abundant isotope?
No.
And why not?
Because you could have like carbon 7 and carbon 17, and that would average 12, but like 12 might not necessarily be the most abundant.
There was one of those on the video. Germanium. It has like
Yeah, that's-
72, like a bunch of those, and then like 174. And so it like rounds up just a little bit to 73, but it's like 90% 72.
Yeah. And bromine is another good example of that. Bromine, it looks like we have bromine 80. However, we have bromine 78 and bromine 79, and we have bromine 81.
Yeah.
We see that with chlorine too. It's chlorine 35 and chlorine 37. Okay. So we're kind of in the middle there. And can we quickly determine which one is more abundant?
Yeah.
Yeah. So like on the bromine, it's closer to 79. So bromine 79 would be slightly higher than our bromine 81. Okay. You could even do your proportions there if you wanted to. Like you have 20-point spread and anyway, or 10-point spread. You know, it's probably close to 60% bromine 79 and 40% bromine 81. Somewhere about that. And I'm doing math wrong in my head, and I shouldn't do it in my head. That's probably closer to 45 and 55. Yep. All right, so what I want us to do, let's use our periodic tables, and let's start working on some of these examples, okay? Should we divide and conquer again today? Let's do it. And so, let's get in 3 groups of 3.
Okay.
So go ahead and move into 3 groups of 3, and I'll let you know which example number you're doing.
Are you gonna say something? You're gonna say even.
I'm sorry. I think.
Okay.
Yeah.
Ray, who do you want to be with?
No.
When was that a trend?
2019.
The
Like 2019.
oh.
No, that was like during
Those were my
lockdown.
glory days.
All right.
2019.
We're looking pretty good on these. Do you have a problem right here with this number of valence electrons? Okay. The 14 you give me is the mass number. So that's your protons and your neutrons. Okay. The number of electrons, or the number of valence electrons specifically, is either 1 through 8.
Give me 1 second. I have my other periodic table right here.
And this is carbon. So let's just all pause here for a second, because on our AP periodic table, we don't have those labeled up top. Okay? But they're easy to write down because you look at the tall columns. Okay? The tall ones, not the short ones. And it goes 1, 2, 3, 4, 5, 6, 7, 8.
So it's 4.
Helium has 2. So carbon is in group 4A. It has 4 valence electrons. Okay. All right. Any questions about that? Okay. Not to say that they're going to put one of these on your AP test, but we do need to have a working knowledge of this as we move forward in terms of talking about the atom. Like, well, how did they know how many energy levels there were or protons there are and things of that nature? I forgot to start recording, and that's probably a good thing. And so, again, what we're going to see here is that magnesium hydroxide, because it really is just the lowest ratio possible, we're never going to see a different percent composition. It's already the lowest. We can't have multiple magnesiums and multiple hydroxides because we just reduce it down to the lowest possible ratio. Those electrons are transferred. They don't go back, okay? Unless there's a chemical change. But on our dinitrogen tetraoxide, all of those electrons are shared. And so they're like attached, so to speak. They've got the electrons in between the different atoms, and they're going to move all as one group. And so that's why we can see the same percent composition, but different formulas actually on molecular compounds. Okay? And that was long and drawn out, but that was kind of where we were going with this. All right, so let's talk about empirical formulas. What were our 3 types of questions that we saw for empirical formulas? Or 1.3 video, 3 notes. What are our 3 types?
I'm
Yeah.
scrolling down like I have it on here.
So like
Keep going.
straightforward, the mass or the percent composition to empirical formula.
I'm gonna write it.
To an empirical formula. All right.
Combustion analysis.
Combustion analysis. And
Hydrate analysis.
hydrate analysis.
I could not figure out for the life of me how to do that hydrate analysis.
Hydrate. I texted Will and he was like,
I did not say that.
Okay, so do we need to talk about the hydrate analysis a little bit more?
You didn't say I don't get it. That's not what you said.
Okay, so I'm going here on this free response that you've already probably got the work down on, okay? On these, are we actually trying to answer the questions first ourselves and then go and see what's right afterwards, or are we just copying it down?
it was hard for me to understand what was really going on. Like I was
Okay.
trying.
It
but I
depends.
didn't-
Okay.
If I understand it,
yeah.
The rest
I
of
didn't
them I
really
did
know.
them.
Okay.
I didn't want to write out the FRQ. I did the rest of them though.
Okay, so here's the thing. That's why I give you the videos that have somebody work it out afterwards. Give it a try. When you get stuck on something, write down, this is where I'm stuck. I don't know what to do next. And then you can go back and kind of check your work on that. And I understand time constraints sometimes. You may be like, oh, free response. I can't do that right now. Let me just try to follow along. I get that. The best way, and I can't tell what you do and what you don't do, but the best way to learn from those videos are going to always be for you to try it first and then see what's going on. Okay? But you know your schedule and you know what you need, okay? So, again, that may sound like I'm coming down on you and mad. I'm not. I'm just letting you know the best, the most effective way to watch these videos is to actually try them first and then go back and correct if you need to. Okay, so let's take a look at our data that we have here. And does anyone remember what we would do to figure out how much water is inside of this hydrated compound? What would we do experimentally?
We're gonna find
Burn it.
the mass. Yeah.
We're going to burn it. And so we got to find masses before and after, but we're going to burn it and not really burn it. We're going to heat it up. Okay. Usually you'd use a crucible over a fire. Again, burn would be chemical change here. And technically we are doing a chemical change, but it would,
You're boiling. Right?
yeah, actually, no, I take that back. We're not doing a chemical change. We're doing a physical change here because we're boiling the water. is we're boiling the water, right?
Grade
So we're gonna
versus-
boil off the water, okay? I would have said that was a best less, but I kind of have forgotten all of those because you bested me.
It was a fun experiment though. I like that experiment.
And we'll do more of that. Like that's gonna be in some labs that we do still. Okay.
So it's like the labs.
So we're gonna need the empty container. Usually it's gonna be a crucible. We've got the sample and the container. Then we have the sample and the container after the first heating. Why are we doing multiple heatings?
Make sure there's no water left.
Yes, we're trying to get all of that water driven off. Okay, and so here, these last two, we're going to notice that we have within plus or minus 0.005, which would be our allowable error. Okay, and so we're going to make sure that we're within those, that amount, and we know that it's relatively steady. Okay, that we've gotten rid of all the water we can, but we haven't started decomposing it yet. Okay. So, again, why can we correctly conclude that the hydrate was heated a sufficient number of times?
There's a negligible difference in mass between heating 2 and heating 3.
Yep, between heating 2, heating 3, they're within the allowable error. There's negligible difference between those, okay? When you give those kind of justifications, we need to hit on some of those key terms, like be specific at what about which trials you're doing, like heating 2 and heating 3. Define that, okay? Don't define it, but write that down in there.
Heating 2, the second time I heated the water.
Yeah, no, you don't have to be that, you don't have to define that. I meant make sure you define which heatings you're talking about. So, or mention it.
Start sweating that third time.
Yes. All right. So now on part B, it wants us to calculate the total number of moles water lost when the sample was heated and then determine the formula of the hydrated compound. Okay. So one of the first things I would do here is let's figure out some of our masses. Because when we see moles, we should think most of the time, start with grams, go to moles. Okay? We saw yesterday in one of our examples, we weren't able to do that because we didn't have a molar mass. So we had to use some other way to get to moles. And we use P equals nRT. Okay? So here, our total number of moles, again, I'm still going to figure out what those masses are. So to begin with, I'm going to have my hydrate, which is the whole thing, the MgCl2 dot, they use NH2O. In my class, we used X just to denote any unknown. They like to use N here because it's technically a number of moles in a mole-to-mole ratio. Okay? And so here, what would we do to figure out just the mass of our hydrate?
The mass of the initial sample and container minus the mass of it after.
Yep. So our before, okay. Not an after yet. Because after we heat it up, do we have the hydrate there? No, the hydrate's going to go away. So I need the before, which is the 25.825. We are going to use that, Emma, just not for the hydrate. What do I need to get rid of?
The mass of the container.
The container. So I've got to get rid of the container, and that's going to be 22.347 grams. And that is going to be, you know, I can't do math in my head.
Even when we're trying to persuade me, it's like, just get the app on your phone, just use that. It's like using the physical calculator. It's like,
So we had 3.478 grams of the hydrate. That's the whole thing. Now, on a hydrate, it looks like it could be similar to a solution because we've got like an ionic compound and we've got water in it. It's not. A solution would be mostly water with our ionic compound dissolved in it. Here we have our ionic compound, and in that crystal lattice, in that lattice structure, there's space. Water molecules can fit in there, okay? And so we've hydrated that. It's our clumpy salt in the summer, which is why you put rice in your salt shakers in the South. Did you know that? Have you ever been to a restaurant where there's salt or rice in the salt shakers? The same thing like with your cell phone. The rice absorbs the moisture and then your salt's not clumpy because of the humidity. All right, so that's that mass. Let's do what we call the anhydrous. What would anhydrous mean?
Anti-hydrate.
But not hydrate.
The not hydrate. Well, what would
Our magnesium chloride.
just the magnesium chloride? Okay, so just a plain old MgCl2. It's what we have after we've heated it. It's left in the crucible. And what mass would we have for that? Emma. You told it to me earlier.
So you do the container before and then the container after.
And you would use that third trial and or the second trial or whichever one you choose. And you would do your before. Okay? So that would be our 23.977 grams minus our 25.825.
The girl in the video, she never calculated the grams for the hydrate.
Yeah.
Yeah, that's what.
That's what I'm looking at. She never calculated for the hydrate. She did something different.
And then for the
She did.
She calculated the grams for the magnesium chloride. Then she had,
Yes.
Then she's like divided by the grams per mole of the hydrate to get like the percent molar of the.
Remember that my job is also to help you think through the problems when you don't understand them, okay? So all I'm doing right now is trying to figure out the mass of all my chemicals that I had. And before I had the hydrate, after what's left over is my anhydrous.
I think you mixed up the numbers.
Yeah, I think you. Because
You
it would
put
be
them in the wrong order.
25.825 minus 23.8.
I sure did. Y'all, I'm sorry. Here we go. Let me fix it.
Nice.
I was like, that's gonna be a negative number.
I mean, technically you wouldn't have to write down.
You have negative magnesium chloride.
And you would just, and you can't have negative mass, so you could have done it that way. And so what are we getting for that anhydrous mass?
That's 1.848.
And I typed that into the calculator just so I could practice my skills.
Yeah.
And then let's find the mass of our water. Okay.
That's
It'd be the
18.82
hydrate
grams per
minus-
mole. Oh, the mass of the water in the solution?
Yeah.
Mm-hmm.
The mass of the
It'd
water
be
is
the
just
hydrate
18.02.
minus the thing, right?
Yeah, you could do your hydrate minus 1.848. Because if you had the hydrate to begin with, you boiled off the water and you're left with the anhydrous, the rest of it should be your water mass. Okay? She probably did, y'all, that's the 1.848. And y'all, I'm so sorry that I'm messing y'all up on this. Not my intent. What did I do wrong with the anhydrous?
You found the amount of water lost.
Yeah,
Yeah.
I found the amount of water lost up there. Okay. And so my apologies on that. What we would need to do.
So it's, oh, that makes sense. It's,
Yep.
it's 1.848 grams of water, and
Yeah.
it's 3.478 minus 1.848 is the amount of magnesium chloride, right?
Yep.
Yeah, okay, that makes a lot more sense. Okay.
That's what y'all are confused about.
I really don't know what's going on.
I don't know what's going on.
was just really confused as to where it starts. Like after she started.
And then you
kind
have,
of
because then you have
walking through,
eighteen
like,
point
the
oh two,
first
that's the
step,
mole of water. You
that's
can
when I
divide
kinda
that.
Yep. What was your?
Divide by the molar mass to get the amount of
For
moles
that,
of
I
water
got 1.630.
in the solution.
Okay. Let's take a look here. Our MgCl2 would have been our final heating, right?
Yes.
Minus your crucible.
Which should still be 1.8.
It's 1.65.
6.5.
Whoa.
Whoa.
That's a new number.
Hang on. You know I can't always calculate.
You
And
put
type-
997 instead of 977.
Yeah.
Thank you.
There we go.
What? Just 6.3.
Oh, it's just 6.3.
Yeah.
Okay. Sorry about that.
Is it?
Okay.
I'm human. I type things in wrong, and it's even worse than what it has been because it's human. All right. So here's the thing that you need to remember about hydrated compounds and empirical molecular formulas. We're looking for a part to a part ratio, a mole to mole ratio of the different parts. So, like if it were dinitrogen tetraoxide, we would be looking for the ratio of moles of nitrogen to moles of oxygen. Here in a hydrate, what are the two parts?
It just clicked in my head.
Well, you have the magnesium and the chloride, but there's also the water to consider, so you have to remove the water in order to get the ratio of
Right.
Cl.
So we do have MgCl2. That's ionic. So the ratio is kind of already set for that. And we're not decomposing the Mg and the Cl2. We are just separating out the part that is the water from the part that isn't water. So you've got your anhydrous. This is one part. There's your other part. You're always going to go to moles of each part. Okay? So question 1 really wants us to take our mass of water and get it from grams to moles.
Yep.
Okay? Then it wants to know what the ratio is to find the formula of your hydrated compound. Well, I need to know the moles of my other part. Okay? And so I'm going to take that 1.630
Yeah.
grams of the anhydrous and go from grams to moles.
The molar mass
That
is
makes sense.
95.21.
95.211. Okay, or 21. We'll just go 21. And that's 1 and 1, and this is 18.02. And that's horrible handwriting. I'm sorry, y'all. Okay, so how many moles did we get for this?
For the anhydrous or for the hydrous?
For the water.
0.1026.
0.1026 what? Apples?
Mm-hmm, exactly, moles.
Water.
I'm afraid of.
MOL.
MOL. Big abbreviation there. Drop
I'll
the
take
E.
it. If I don't have to write the E,
So
I'll
that's
write it.
1A. Okay? Now, y'all, remember too, I'm trying to have you work through this mentally in your head. Will it take you as long as what we took on subtracting, hopefully? No, but find the mass that you actually have of each of your chemicals. So get rid of your crucible or whatever container it is pretty quickly, okay? You could even just put it up there in the data table rather than here if you need to, okay? Then we saw, oh, it wants to know moles of the water. Well, let me figure out what my mass of my water is. Then I can convert to moles. Part 2 wants us to find the formula, correct? Which means I'm going to need a ratio of waters to magnesium chloride. I need that mole of magnesium chloride. Let me put that up there with that. Okay. So what is my mole How many moles of magnesium chloride did she give us?
5.992. What's she?
0.01722.
And you are going to end up with a 5 out in front of your waters, okay? So technically, we have a ratio here. It's 0.1026 to 0.01722. Is that a nice ratio, though? No, and the nice thing about ratios is we can kind of do whatever we want to them as long as we do it to both parts of the ratio. And so the easiest thing to do is to divide by the smallest number of moles. That's going to give us 1. Okay? So I'm going to divide by the 0.01722, and I'm going to divide my 0.1026 moles of H2O divided by 0.01722 moles of MgCl2. And I don't really have to put moles of MgCl2 there. I'm just trying to get the ratio. And our ratio here, what did we end up with for that?
992.
You can round that up.
Up to 6.
Okay, so 5.992, which rounds to 6. Now, general rule of thumb, take a look at the 10th place. If you round to the 10th place and it rounds up to a whole number or rounds down to a whole number, you're pretty good. Even if it's like 1, like 0.1 or something like that, or 0.85, we're good. If it ends in like 5.5, we would have to multiply by 2 and multiply both of them by 2 to get a whole number ratio. And so this would be 6, and we would say MgCl2.6H2O. Okay? That make a little bit more sense on what we're doing? To find a chemical formula for mass data or percent data, figure out what your parts are, convert to moles of each part, divide by the smallest number of moles to get hopefully a whole number ratio. If it's not there yet, multiply by a coefficient of a whole number ratio, okay? And then that should give you your ratios. So moles of each part, divide by the smallest, get a whole number ratio, okay? Again, if it's for elements, do it for each element. Here on a hydrate, our 2 parts are water and the anhydrous. Okay? All right. That should help out. And in fact, let's go ahead and do example 7. Because that's another hydrate.
So his light work.
It is, but look, it's the mass of the hydrate alone before heating. So it's just having you find that.
That's 2.500.
Is it actually?
Oh, it says, and answer the following questions, and there are no questions. I'm so sorry. They must have gotten deleted. So we're going to do 1 is going to be to find the mass or the moles of water. And then your formula of your hydrate.